Okay. So with periodic boundary conditions, your Floki unitary over one period is exactly the identity, nothing happens, okay? So that's this blue spectrum right there. But now, imagine that you opened your system up and you created an edge. Then what you see is that if you start with this, if you start with the particle that lives on that white circle right there, okay, you act with 1, this goes to this red, this goes to this black one right here. Then over the next period, nothing happens, you know, there's no bond acting on this edge over here, so it just stays there. Then on period 3, you see that it moves over 1 more, and then in period 4, nothing happens to it, okay? So a particle in the bulk that starts off here under the action of this unitary enacts this closed loop, but something on the edge just hops over 1 unit cell. Okay, and if you repeated this for this bottom edge, it would hop over in the opposite direction. Okay, so this is very much like when you think of a quantum Hall system with an edge. You know, there's this picture which is very famous of all these cyclotron orbits. Right, so in a quantum Hall bar, you know, in the bulk you can have these closed orbits, but then along the edge you'll actually get something that skips along like that, right? Okay, so in a quantum Hall system, if you had periodic boundary conditions in both directions, so this is now I've made this semi-infinite, but I've made it on a strip, right? So in a quantum Hall system, if the closed periodic system had a non-zero Chern number, and then you opened it up like this, you get these edge modes, okay? What we're seeing now in the Floki system is that with periodic boundary conditions, even though you had a completely trivial Chern number of 0, a completely trivial evolution, you can nevertheless get these edge modes, and they really just come from this kind of winding in the micromotion of the problem. Okay, so this band structure is allowed in a Floki problem, and this is consistent with this Chern number being 0 while having a right moving and left moving edge. Okay, so is that clear? Yeah. That's right, and that's the point. That, yeah. No, I had, so in the intermediate times it had e to the minus I HFT times this object here. And that's this micromotion operator, which is really important. Exactly. So this phi of t, when t is 0, so this phi of t is periodic in time. And using the fact that u of 0 is the identity, we know that phi of 0 is 1, right? So if you look at u of capital T, that's the definition of the Floki Hamiltonian, it's just equal to that. But if I only looked at u of capital T and h Floki, I would get something that was trivial. But if I look at this full object with the micromotion, then I get this non-trivial winding, and I can get those edge modes there. So that's the point. Okay? Good. So the other thing that's really nice about this model, which the same group of authors, maybe with a few more, showed, is that you can actually take the system and it's stable to the addition of disorder. Okay? And what you can get is, you can get a band spectrum where your bulk looks completely localized, but you can nevertheless get these delocalized edge states, okay? So, again, in this problem, you know, this part here, you know, so this is a 4-part drive, you go from 1 to 2 to 3 to 4, and then in the 5th part, there's just something on site, okay? So your particle just stays where it is, it just picks up some diagonal on site energy. But you can make this completely disordered, okay? And when you do that, what you'll find is that your bulk bands, you know, the states that started off living where they are, they continue to be good eigenstates. They're all localized, but the edge states still show you this delocalized chiral motion, Okay? This is different from the quantum Hall problem, where if you have delocalized edge states, you know that you have to, and then you add in disorder, you can get Anderson localization. So even though the vast majority of your bulk states can look localized, you know that somewhere in the bulk there has to be a delocalized edge mode, okay? And that can follow just from using the same kinds of spectral flow arguments that Joel was explaining, because what happens is that as you're trying to pump charge from one edge to the other, say in this disk geometry, okay, you have all your eigenstates that move, and instead of getting these states to just run away, like you have an edge state that's coming down, you have an edge state that's coming up, and they have to merge with some delocalized gapless, or they have to merge with some delocalized bulk mode to actually do this pumping. But in the Floki problem, what can happen is that you don't have this runaway to infinity. You can just have this edge state that can pump all the way across and come back to across the Floki-Brillouin zone. Okay, so this is the case where you can get a completely localized bulk spectrum while also getting delocalized edges. So the authors called it an anomalous Floki-Anderson insulator. Okay. Good. So let me actually before moving on, where's the let me just complete this example because it'll be useful for things we'll do in the future. Okay, so you can take this, and over the four cycles that this is going through, right, you can write it as j of t e to the minus I k dot b. These b's are lattice vectors along the spatial lattice. But then you can write this as some sigma plus operator, and then you have the Hermitian conjugate. And then there's some on-site delta AB sigma z. Okay, so this sigma plus and sigma minus, they live in this internal space that transfers things from the A sublattice to the B sublattice. And the way this problem was set up is that this j of t is basically 0 except for, in the first period, these j's are non-zero. In the second period, these j's are non-zero. And it's further tuned so that jt over 5, because you've divided your whole evolution into these 5 steps. So when you write your Floki unitary, right, this is the time-ordered exponential. But if your system is piecewise constant, you can write it as e to the minus I h1, e to the minus I h2, e to the minus I h3. Right? And we've broken it up into 5 equal periods. Okay, so that's what a Floki unitary over 1 period looks like. And now if we pick it so that jt over 5 is exactly pi over 2, okay, what you can end up getting is this piece of it looks something like minus I pi over 2, some sigma plus sigma minus. You can keep going, okay? And this is on the particular bond that we care about. Let's call that bond red, right? So what that does is that when you act with this evolution, now e to the pi over 2 times the Pauli operator, you can expand it out as cosines and sines. This just ends up being proportional to sigma plus sigma minus, okay? So what you end up getting then is when you act with this part of your drive, if you started with a system if you started with a particle exactly on this site, you act with sigma plus, that takes you from the A sublattice to the B sublattice, you enact a perfect with probability 1, this particle moves over to the neighboring site, okay? So that's how by tuning your Floki parameters, you can get this kind of evolution to work out, okay? And then because this is really the intrinsic features of this are coming from this wrapping of this edge mode around this quasi-energy spectrum, once you move away from these exact values, which were fine-tuned to be jt over 5s pi over 2, you'll still, you can now start messing with what this bulk band is doing. You can give it some dispersion, but the fact that you have these edge modes will remain. Okay, so that'll be stable in that sense. Okay, good. And something that I'll come back to in a second is when you get non-trivial phases like this, right? Like that's a spectrum. If you see that quasi-energy spectrum, that's not a spectrum you can ever write down for a static problem. Okay, it's a spectrum that's only well defined in the Floki setting. And when you see things like that, it's usually when your parameters in your Hamiltonian, in this case j of t, are comparable to the frequency. Okay, so in this case, you can see that the frequency is 2 pi over t. So j is so this is pi over 2t. This is omega over 4. J is 5 omega over 4. Okay, so j is comparable to omega. So when your driving frequencies are comparable to the intrinsic scales in the problem, then you can get non-trivial Floki phases. And what I'll show you in a second is when your frequencies are much bigger than these intrinsic scales in the problem, that's when you get kind of trivial static Hamiltonians. Okay, so yeah. So this is just telling you. So these are different lattice vectors. Okay. Yeah, k dot b. B, yeah. And b's are different lattice vectors along the different directions. Okay. Okay.
Sorry, could I ask you?
Yeah.
So how does the constancy of this piecewise
right. Yeah. Yeah.
affect the quasi-energy spectrum? Can you make the link more concrete for school?
No, so the constancy was just used as a tool to get an exactly solvable problem. So with this constancy, what you can see is that if your system had exactly closed boundary conditions, okay, then your unitary is just 1. Okay, but if it was more general, like if it had some j of t, which was like some cosine, you just have to work harder to solve it.
Okay. But
okay.
Then the quasi-energy spectrum would be what? I mean, let's say,
yeah.
How would
yeah.
this translate if you had like a periodic instead of a constant?
Right. So the point is that weak perturbations about this are supposed to respect the phase. Okay. So that's the topological aspect of it. Yeah. So even if you don't have exactly this, but something that looks like it, where j is still comparable, j of t is comparable to that, then you'll get then you should get something like that. Yeah. Exactly. Good. So now let's do the repeated, so that this was already anticipated in some of the questions. So this is like a repeated zone scheme in the Floki Brill1 zone. Okay. So now what we can do is, so just again, when you have spatial periodicity, you can either define a momentum within a single Brill1 zone, or you can have momentum be continuous, but then have everything identified, right? Like, so every k is identified with k that differs from it by multiples of the reciprocal lattice vectors. So likewise, we can now start doing something similar in Floki space. Okay, so if you have a ht which is periodic, we can write the Fourier series of this. Okay. And these Floki states that were defined in terms of these periodic, these were like the u's in the usual block theorem. These are periodic in time as well. So you can write them also in this way. Okay. So now we take this h of t and this phi alpha of t, plug it into the time-dependent Schrodinger equation, equate different frequency components, and now what you get is going to be something that indeed lives on this expanded Hilbert space. Okay, so what this is doing is you've now taken your original Hamiltonian, which lived in some Hilbert space H, but your new Hamiltonian now lives in this very expanded Hilbert space. You made infinitely many copies of it. Okay, so this is what you were anticipating earlier. And now your problem, this is called, your M is a replica index. And what this looks like is that your Hamiltonian is actually hopping you between different replicas, okay? But then you also have this potential in replica space, okay? So if you just think of M as some new effective site, right? So this is the hopping term, because you want to get the eigenstates with that M. This is M minus P. So this is the hopping term in this new site index. And this is an on-site potential. This is like this is what's called a one-year Stark potential. Okay, you can see that your different replicas are distinguished by this this term, which grows linearly. So that's M equals 1, M equals 2, and this is going to quantify kind of how many photons you're absorbing from the drive. Okay, so again, let's make this a bit more concrete. Yeah. Mm-hmm.
We are looking for the sector which quasi-energy fixed. Do you understand the question?
You're looking for a sector with fixed quasi-energy.
What is omega? Is 2 pi over frequency?
Omega is 2 pi with the frequency. Yeah. So, okay, so then let's take a Hamiltonian, which is h of t is h naught plus some okay, so this is a Hamiltonian, this is another operator, that's another operator. Okay, so this is like if you had a Hamiltonian which was some h naught plus v cosine omega t, for instance. Okay, then you can write it like that. Okay, so what you can now do is, let's take the Hamiltonian, write it in this kind of space, okay, and what you'll find is that, so that was h naught. Okay, so the e to the I omega, e to the minus I omega, that tells you that when you go to Fourier space like this term delta couples you between things that differ in one index of M, right? So what you have here is, so this is M equals 0, this is some M prime equals 0, and this is plus 1, minus 1, so you have delta dagger. This piece picks up an h naught plus omega. There's another delta. Here you have an h naught minus omega, and so on. Okay? So this gets repeated all through, but basically this is the on-site diagonal piece that's time independent, okay, in this language. And this is picking up this kind of one-year Stark ladder where you're going from h naught minus 2 omega to minus omega to h naught plus omega and so on. And then you can hop between, because of the Floki driving, the point is that because you now have this time periodicity with period omega, you can now absorb energy in these quanta of omega. And that's what this term is trying to do. Okay, so that's the replica of your system where all your energy has kind of been shifted over by 1 omega, 2 omega, and now you can start coupling between these using different deltas. Okay, so for instance, what this means is that if you had a spectrum for h naught, okay, so if your h naught had some spectrum which was like this, okay, now what you can start doing is you'll take this spectrum, so this is, say, the m equals 0 spectrum of h naught, but now you can take this and you'll keep adding, you'll keep shifting this over by units of omega, okay? So that's like this repeated zone scheme. You can just take this and move everything by integer multiples of omega. So for instance, so this is one copy, and then you can have the shifted over copy that intersects with this once you move this by omega. And then that will continue forward again, so you can have another copy which is moved over by another omega. Okay, and then you have this guy, and this can move down now. So, right? So what that does is, as a result of the driving, your energy is only defined mod omega. Okay, so all your different bands, you may have had a band gap to start, but now this band gap is only defined mod omega, so you fold everything in, and now you can end up creating all these resonances between states that differ by multiples of n omega. Okay, and now when you act with this delta, what you'll do is you'll open up gaps here in the usual way. Okay, and you can use this to now solve this eigenvalue problem and get your Floki eigenstates, which are your phi alphas. These are the Fourier components of it. Okay, and you might say, okay, where's the free lunch? I've just made this problem infinite dimensional. So how am I actually going to solve it? And the point is that now what you can do is things like, because you have this kind of this one-year Stark potential, right? Like if you want to absorb 2 omega, right? You have this potential energy that's really growing linearly in time like this. So you actually have your wave functions. You know this from non-interacting Stark ladders. Your wave functions are localized in M space. Okay. So in practice, what you can do is you can take this infinite system and you can actually truncate it at some order, okay, and get a pretty good approximation to your exact eigenstates because your system is localized in this replica space. Okay. But intuitively, what we're really doing here is when you're, so this is this comment that I made about large frequencies and small frequencies, okay? Yeah, so if you have a single particle problem, so let's just do a problem where H is C dagger I, Ci plus 1 plus HC, and then you have a sum over, and there's a potential here that scales as I like that, okay? So this is just a 1D tight binding problem. So your on-site potential looks like that. Okay, so this is like if you had a constant electric field, for instance. Okay, so if you want to stick your system in an electric field, that's your potential gradient. Okay, so if you have a system like this, this is what's known as a one-year Stark ladder. Okay, and these lead to localized wave functions. So you can solve for this, your solutions, your eigenstates will look like Bessel functions. Okay, and the main point is that you're going to try to hop between these different sites, but then you have to pay this energy penalty because you have to climb up this hill. Okay, so then you kind of stay stuck. So here what we've done is by taking this Floki system, you've basically mapped it into this extended zone scheme, but with this kind of in the single particle language, you have this one-year Stark potential. And so you can truncate it to some order. Okay? Good. So using this, we can actually now understand this comment that I was making, that if you want to get something non-trivial, you need your couplings to be comparable to the frequency. Okay, so when omega is much, much bigger than J, or actually more precisely the bandwidth, and you'll see that once you do a many-body problem, you can't actually do this. Okay, so once omega is much, much bigger than your bandwidth, then you basically have an H Floki that looks well-defined or static. Okay, and what's happening is that you have some bandwidth in your problem which is set by J. Okay, so say your energy is lived within some bandwidth j. And now if your frequency was omega, which is much, much bigger than j, right? Then you can take this spectrum and you can move it up in units of j, but you actually aren't creating any of these resonances, right? Because this will just never overlap. You take it, you move it over by j, you create something way far out here, you move it up and you create something over here. But basically the spectrum looks very much like whatever it used to be for H naught. Okay, by doing this repeated zone, you're not really bringing states at different frequencies into resonance with each other. Okay, so put differently, J sets the local energy scale in your problem, right? It tells you how much, like if you make this move, like if a particle hops over 1, what's the energy that you can absorb, right? And if your frequency omega is much bigger than this local energy scale, well then it's just, by making these local moves, you really can't absorb that frequency. Okay, so that's why when omega is much, much bigger than j, you really don't couple between these different block bands, and your Floki Hamiltonian to leading order just looks like whatever it was in the time average sense, and then it'll just get dressed a little bit. Okay. On the other hand, if you had some bandwidth, which was the picture I was drawing there, which was like this, okay, and this is j, but omega is quite small, so that was omega. Then what you can start doing is you'll take this bandwidth and you'll move it over in increments of of omega, but as you do that, you'll make all these overlapping bands, and then you'll actually be absorbing all these different quanta of energy, okay? So that's like, if you can absorb energy in units of omega, and your actual local energy scales are bigger than that, well then you can very efficiently absorb lots of photons. Okay, so this is a heuristic picture for how this Floki heating happens. You basically want to bring energy levels that differ by mod omega into resonance with each other. You'll open this gap up, and then your new eigenstates are a mixture between eigenstates that in the undriven problem differed by multiples of omega. Okay, so that's what's causing your heating. So to put this in a different language, there's something known as the Floki Magnus expansion, which we'll use quite heavily. Okay, so that's what it is. But this is now coming back and making more precise this definition of the Floki Hamiltonian that I had mentioned earlier. Okay, so you have the time evolution operator. You have u of t, which is the time-ordered exponential of h of t, and I'm using this to define the static Floki Hamiltonian so that u of t looks as if it was being evolved by this time-independent Floki Hamiltonian. Okay. Now we can tailor expand both exponentials, equate them order by order, okay? And what you'll find is that the leading order term in the Floki Hamiltonian, and I'll tell you what this order is actually just the time average. Okay, so this is defined as h naught. So what you'll often do is you'll rewrite your drive as h of t equals h naught plus v cosine omega t, and you want to think about whether the properties of your system are well described just by thinking about h naught, or if these other terms can actually come in and make a huge difference. Okay, so that's the first order piece. The second order looks like, sorry. Right, this is just, you have a time-ordered exponential, you have the expansion for it, okay? But note that the subsequent orders in this expansion, this is really a high-frequency expansion, okay? Because you notice that at first order, you have two integrals in time, okay? So this is the factor of t squared, and you have one t living in the denominator. So this basically goes as t squared over t, which is t, which is 1 over omega. Okay, so the first order piece is 1 over omega, the second order piece is 1 over omega squared. So this is really your Floki Hamiltonian has this expansion which looks like 1 over omega to the n, h Floki to the nth power. Okay, you can define an expansion of that form. Okay, so now the big question is this expansion convergent or not? Okay, and the point is that when you have a single particle problem, then these terms here, these Hamiltonians, they themselves have some norms. Okay, they have an operator norm. And when your system is a single particle problem, then the bandwidth of this Hamiltonian is just some order 1 energy scale. It's just something like J or T, right? It's just order J or order T, some hopping. Okay? So in that case, if your frequency is much, much bigger than this bandwidth, then this expansion actually can be made convergent. Okay? So what that means is you can define a Floki Hamiltonian, which to leading order looks like the time average, and the higher order terms just give you corrections that are subsequently smaller and smaller. Okay, so this is what experimentalists use when they're trying to do Floki engineering. Okay, so they want to get some desired H naught, and they may not have access to that H naught as it is, but what they can do is, again, maybe in this piecewise continuous way or maybe in a time periodic way, they can engineer Hamiltonians which, when time averaged, give them the H naught that they want. Okay. And then if this turns out to be a good expansion so that the subsequent terms are smaller and smaller, then it looks like your evolution is really governed to leading order by that object. Okay? And then the phases and so on that you'll get for your unitary will just be the phases that you would have gotten for some dressed version of H naught. Okay, so that's the type 1 Floki business. On the other hand, the interesting behavior is when your drives are not high frequency. Okay? So when your drives are not high frequency, this expansion does not converge, okay? And then you can't write, so then your different terms, which are very, very non-local, each higher order term involves commutators over more and more Hamiltonians, right? And these commutators cause the range of the Hamiltonian to grow, okay? So if your frequency is not large, then this expansion is not convergent, which means the higher order terms, which are much, much more spatially long ranged, are coming in at about the same order as your low order terms. Okay? So this is just not a well-defined local Hamiltonian. Okay? But it's precisely in those cases that you actually end up getting new kinds of Floki phases. So that's like the example that we did with the hopping. We had J, which was the same order as omega. Okay? So this expansion was not going to be convergent, and that's why you got this band structure which basically looks like this, which doesn't look like the band structure of any static H naught. It was something that was intrinsically new. Okay, and this is also the reason why you get heating in a many-body system. So in a many-body system, your bandwidths, which are the norms of these H's, your bandwidths are extensive in the system size. Okay, so your frequency, you always want your frequency to be much, much bigger than some bandwidth to get the Floki Magnus expansion to converge. Right? But in a many-body problem, this bandwidth actually scales as system size, whereas any sensible frequency is going to be order 1. Okay? So you can never get this expansion to converge in a many-body Floki system, except when we come to many-body localization. Take your question in a second. So the generic answer is that when you have an interacting system, this bandwidth is scaling with system size, the frequency is scaling as some order 1 number, so this is never satisfied. So this expansion is never convergent, okay? Right, so that's a restatement of the heating result, that you cannot describe your system as the exponential of some local static Hamiltonian in a many-body system. But what we'll find, and I'll come to this next lecture, is that this actually forms what's known as an asymptotic expansion. Okay, so even though it's ultimately divergent, it can look convergent up to some optimal order in this expansion when your frequencies satisfy something like, they can be much, much bigger than the local energy scales of the problem, but much, much less than the many-body bandwidth, okay? So in this order of limits, what you can get is something known as pre-thermalization, which tells you that even though your system is eventually going to heat up to infinite temperature, it can take a time which is very, very long to do so, okay? And the picture for that is you have a local Hamiltonian and a local drive, and even though you're ultimately heating up to infinite temperature, you're doing so in units of J, and if omega is much, much bigger than J, then you need to do a very high order process, you keep doing lots of J's to absorb one quantum of energy, so that's something that's suppressed, and that high order process gives you an exponentially slow heating rate, so that this expansion looks convergent up to some order which sets the heating time, and then beyond that it looks divergent, okay? So there's
on the convergence issue,
yeah.
so
Yeah.
In the rewriting of this formula
Yeah.
kind of L,
Right.
how do these commutators scale with L? So then we can judge on the convergence of the series like the
So ignore this line, because this L is something different. So the HF of T naught just has one commutator, and then HF2, the second order has three the first order has two commutators, the second order has three commutators. Okay.
Just one thing.
Yeah. And the point is that if you have a Hamiltonian which is a sum of local terms, each time you take the commutator of that Hamiltonian with itself, the range of the Hamiltonian will grow, right? Is that clear why that happens? So each of these terms which involve more and more commutators are longer and longer ranged, and they're coming in at a higher order in 1 over omega, okay? But then to actually get this to converge, we want the norms of each of these terms to go down in 1 over omega, but when these norms are many-body, so when this is extensive in system size, you can't compensate for an extensive norm with an order 1 frequency, and that's why you get heating. But when you have a single particle problem, you can actually get this convergent Magnus expansion. Yeah. Okay. So can I go for 10 more minutes, or should I stop? Yeah. Okay, all right. Okay, so before we end, I just want to present. So we saw this one toy example, which was this anomalous Floki-Anderson insulator. And before we end, I just want to present one more toy example that we'll actually come back to several times, which is the driven Murano chain. Okay, so maybe I'll just give you the highlights. Okay, so when we have a static transverse field Ising model, okay, so your H looks like J. So these refer to Pauli operators. Okay, I'm just a shorthand for sigma I z. So zi plus 1, sum over I, minus H xi. Okay, so that's the usual transverse field Ising model. This has Ising symmetry, which corresponds to taking all your spins and flipping it in the z basis. Okay, so the transverse field Ising model is mappable via Jordan-Wigner transformation to a system of free fermions. Okay, so you can take this and you can rewrite this as some u times a dagger I plus ai, and right. So Okay, so these are now, so everyone's seen the Jordan-Wigner transformation, right, which takes you from spin variables to fermionic variables. Okay, so these A daggers in fermion language, when you map them to spin language, they look like some raising operator for the spin with some Jordan-Wigner string, which has a bunch of these x's. Okay, so this is this free model. You can see has terms like A dagger. This doesn't conserve particle number, but only conserves particle number mod 2. Okay, so that's the parity. So this is a Z2 invariant, which corresponds to the Ising flip symmetry. In fermion language, this maps to the parity, whether you have even or odd number of fermions. Okay, and you can take this system. This is a P wave, the Kitaev P wave superconductor, and you can write this. And you can solve it by writing it in Murano language. So now what you do is you take your fermions A's and you split up each site into 2. Okay, so for a site J, you have 2 Murano fermions. So this is C2J minus 1, C2J, and you can write these as and these are real fermions, okay, with the same commutation relations. All right, so what this buys you is that when you take this Hamiltonian written in terms of your A's and A daggers, rewrite it in terms of fermions, what you find is that these bonds, right, the bonds that act between Murano fermions that live in different sublattices, these are your J's, okay, and these bonds that act within the same cell, those are your transverse fields H. Okay, so in the Ising model, of course, we know that when J is much, much bigger than 8, you have a ferromagnet, right? So that's the phase which shows non-trivial order. For your ferromagnet, so when H is 0, you have a completely degenerate spectrum, right? But in general, you have a ground state degeneracy where these two states, which are Ising symmetric, but they're even in odd cats, they're related under the action of the Ising symmetry, and the splitting between these states is something which is exponentially small in system size, okay? And what that's related to is the presence of this 0 Majorana edge mode, okay? Because when you write this in Majorana language, you can show that your spectrum can actually be written in a form where you have some Majorana operators once you diagonalize the spectrum, and then form these Majorana operators, you can form your new fermionic operators, which will look like some A twiddle dagger of K, A twiddle of K, okay? And the spectrum has particle hole symmetry, so all your eigenstates, so you have the eigenstates all come in pairs, like plus or minus epsilon k, so there's a redundancy in the spectrum. And what this shows you is that epsilon equals 0 is special, okay? So what you'll do is when you draw your single particle spectrum, you have a bunch of states, and then you have the same states but reversed, but then, you can have two states that are your Majorana 0 modes, okay? And these states correspond to, in the ordered phase, they correspond to an edge mode that lives on this edge and an edge mode that lives on that edge, okay? So by toggling the occupancy of the fermionic mode formed by those edge modes, you toggle the fermionic parity, which corresponds to toggling the Ising parity in spin language. Okay, so the degeneracy between this state and this state, the plus and the minus, which is exponentially small in spin language, corresponds to this being an exponentially small splitting. So these states are exponentially close to 0. Okay, so because you have this E to minus E particle hole symmetry, E equals 0 ends up being very special. Okay, so in the Floki case, what you'll find is that not only do you have Majorana 0 modes, right? So these are called Majorana 0 modes. What you'll find is that the condition that E equals minus E can actually be satisfied at a different value of quasi-energy, which is E equals pi over T, right? Because pi over T is now also identified with minus pi over T. So when you look at the driven Majorana chain or the driven transverse field Ising model, what you get is not just a Majorana 0 mode, but you get a Majorana pi mode as well. Okay, so you have an edge mode that's at 0 quasi-energy and it's localized on those edges, but you have a different edge mode that's also but that has a quasi-energy, which is pi, okay? So now you can classify your system based on the absence or presence of not just 0 Majorana modes, but 0 and pi Majorana modes. And we'll come back to this when we discuss the driven Ising system. But what this tells you is that here your spectrum had a degeneracy, and in this case your spectrum will, in the spin language, will have a pairing with a quasi-energy spacing that's separated by pi. Okay, so I just wanted to flag that, and I'll come back to that example in the future lectures. Okay.